Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be looking at a method to solve the classical mechanical models, namely the method of perturbation and asymptotics. So the perturbation methods. So this treatment will be more mathematical in the sense that we will be looking at more toy problems in order to solve and highlight the method, the solution methodology. And then this method can eventually be used later on to solve real problems in classical mechanics. So as I just said, the topic of our discussion today is perturbation methods. Perturbation methods. So we will see that there are mainly two types of perturbation methods. One is the so-called regular perturbation. The other one is the singular perturbation. So we start with the more easier treatment, that is the regular perturbation methods. So regular perturbation. Okay, so the goal now is we will highlight this method of regular perturbation using a simple algebraic equation. The equation that I have in mind is this following quadratic equation: x square plus 2 epsilon x minus 1 is equal to 0. And the goal of the problem is to find an accurate approximation of solution in solution x in x of this problem, right? So let me call this problem as 1. And if we were to look at this problem, well, one way is we can directly solve this quadratic equation and we'll get an exact solution, but that is not the idea. The idea is we are going to use some approximation because eventually we will see that our problems of interest will not be as simple as the one shown here, right? So we will not be able to solve exactly. So the first step in the solution methodology is we can separate out all the terms which does not have any epsilon and club it in one side and put it on the put the terms having epsilon on the other side, right? So now we see that on one end, on the left hand side, we have a parabola. So if we were to plot this parabola, we will see that the parabola cuts the x-axis at 2 points, +1 and -1 and +1. And on the right hand side, we have a straight line which is going to be, well, this is not the one. Which is going to be this following, right? Okay, so which is going to be the following. Okay, so we see that so given this slope of -2 epsilon, we see that there is one root which is, so let's say there are two roots, R1 and R2. We see that R1 will be of this solution, the R1 root will be less than -1, right? So this is my R1, and we will see that R2 will be less than 1, and so this is my R2, and of course it is greater than 0, right? We are treating epsilon to be a very small parameter here. Okay, so as I just said, one way to solve this problem is to directly solve it and expand in epsilon, where epsilon is a small parameter. So the first step, which is going to be discouraged later on in more, and of course in more complicated problems it will not be possible, is to solve and expand. So we can directly find the solution to this equation, and we see that the two solutions, x is minus epsilon x plus minus square root 1 plus epsilon square, right? And we see that 1 plus epsilon square under the root is 1 plus epsilon square by 2 minus epsilon 4 by 8 and so on. So we have used a binomial expansion in this square root. Okay, so now if we plug this expansion, we see that this is going to be minus there is no x here, so this is minus epsilon plus minus this. So we now see that this is going to be minus epsilon plus minus 1 plus epsilon square by 2 minus epsilon 4 by 8 and so on. And so if we were to write this is going to be rewriting it is going to be plus minus 1 minus epsilon and then plus epsilon square by 2, plus with a plus minus, and then will minus plus epsilon 4 by 8 and so on, right? The important thing to note is that if we were to look at the order, if we want to see the leading order solution to this problem, the leading order solution is epsilon to the power 0. We see that the two roots are plus minus 1. As expected, that is going to be when we put epsilon equal to 0, the two roots are the roots of the parabola. And then if we have epsilon to the power 1, the order epsilon solution will be plus minus 1 minus epsilon, and then we see that this is going to be, we see that one of the root is, as expected, one of the root is less than minus 1 and the other root is less than 1. So epsilon to the power 0 and epsilon to the power 1. So the observations is matching with the expansion. So now the problem is, the limitation of this first method is that we need to solve the entire equation in order to find the expansion, and that is not possible for very complicated problems, as we will see in the next example. So let me write down the limitation. The limitation here is, that need to solve complex equation before approximation, and this is not possible for very complex problem, right? Not possible for very complicated problem, which we will see soon. Okay, very complex problem. Okay. The second method that I really wish to focus in this solution methodology is to first expand the unknown in powers of epsilon and then solve. That is the other way around. So method 2 is the essence of regular perturbation. So we first expand and then solve. So let us assume the solution methodology is x epsilon is x of 0 plus epsilon x prime 0 plus epsilon square by 2 x double prime 0 and so on. So this is the Taylor's method, right? The Taylor series expansion, and we have used just the power series method. Okay, so we have expanded about epsilon equal to 0. So then we could possibly write down that this x is, so this x is x0. So x0 is x at epsilon equal to 0 plus epsilon x1. x1 is x prime at epsilon equal to 0 and plus epsilon square by 2 x2 and so on. So we have now renamed our unknowns as x0, x1, x2 and so on. So now if we plug, so let me call this expansion as 2, and if we plug 2 into equation 1, we see that we are going to get the following series. We will see that this is x0 plus epsilon x1 plus epsilon square x2 and so on times, so this is whole square plus 2 epsilon, I'm just using equation number 1 and plugging the series 2 in there, plus epsilon x1 and so on plus epsilon square x2, and then minus 1, this is equal to 0. So this is my entire equation that we are solving in the series form. Okay, so then order 1, if we were to look at the epsilon to the power 0 order solution here, we will see that the solution is x naught square minus 1 is 0. So here is one 0th order term, the other one is here. The rest are all multiplied with powers of epsilon. So we see that the solution comes out to be x naught is plus minus 1. And now similarly, if we solve order 1 epsilon to the power 1 expansion, we will try to club all the order epsilon terms. In the square, we get the following terms: x naught x1. So there is an epsilon which is multiplied outside. X naught x1 plus x naught is equal to 0. So here is one term we multiplied with epsilon, and there is here is another term when it is taken a square to be x naught x1 twice multiplied. So the twice has been factored out, we can say this. Okay, so now if we plug x naught into this second solution, we are going to get that x1 well, x naught is not, we know that x naught is not 0, it is plus 1 or minus 1. So from here we can quickly deduce that x1 is minus 1, right? And similarly we can continue solving order epsilon square term, order epsilon cube term and so on, right? And finally what we are going to get is that the final expansion is we have found x naught, so x naught is plus minus 1. We have found x1, so this is minus epsilon, minus 1 times epsilon, plus some higher order terms which we haven't solved, and so on. We can continue solving these for each orders of epsilon, and we will continue to get the solution. So again, we see the properties remains unchanged. The 0th order term has the roots plus minus 1, and the first order epsilon to the power 1 order term has roots which are less than 1 and less than minus 1, and the properties will continue. So we see that the regular perturbation, so this is my regular the regular perturbation method, I will call it as RP, and this is the essence, that if we can use this regular series expansion to find out the solution to this power series, and that's it. So so the important thing to note is the regular expansion, the regular perturbation method. If we look at this problem, it is only going to work if epsilon is not multiplied to the highest power or highest order derivative in the equation. If epsilon is multiplied to the highest power, suppose it was multiplied with x square, then the regular perturbation method will not be possible to be used, because we will run into some serious problems. We will see very soon. And so that is the essence between, that essential difference between regular and singular perturbation. So we need to see where is epsilon multiplied. Is it multiplied with the highest order or the next one or the lower order terms, right? So now let us try, in regular perturbation we should be able to understand what are the expansions of the functions. So let us look at some common expansions which will aid us in using this method in solving problems. So let us look at some common expansions of functions. Expansion of functions. So the first example is f of epsilon is sine of pi by 6 plus epsilon, right? And the Taylor series comes out to be f of epsilon. F prime epsilon is, again, if we were to use the Taylor series, the first derivative will give us cos of pi by 6 plus epsilon, and f double prime epsilon is minus sine pi by 6 plus epsilon, and so on, right? And if we now start to use this Taylor series at epsilon equal to 0, then we see that f epsilon has this expansion of the form f of 0. So f of 0 is sine of pi by 6, which is 1 by 2, and then plus the next term will be epsilon f prime at 0. We can start plugging in the value 0 in this functions, plus epsilon square f double prime 0 by 2 factorial, and so on. So if we were to write the series expansion, we see that this is half plus half square root 3 by 2 epsilon minus 1 half square epsilon square, and plus, and so on. So that is quite easy for this example. Our next example is slightly more involved. For example, look at this problem here where we take f epsilon is equal to log of 1 plus square root epsilon, right? We see that the Taylor series, well, if we were to use again the Taylor series, we will see that we will run into problems from the first derivative onwards, because the first derivative will not be defined, right? So we will see that f prime 0 not defined. Okay, so if we do that, so what to do then? What we can do now is we can take y, we can do a variable substitution, y is equal to square root epsilon, and expand around y equal to 0. So we have log of 1 plus y is equal to y minus y square by 2 plus y cube by 3 minus, and so on and so forth, right? So what we have is log of 1 plus square root epsilon. Now if we plug back y, we get that this is square root y minus y by 2 plus epsilon by to the power 3 by 2 by 3, and so on. So just using a quick substitution of y equal to square root epsilon and using the log expansion, we have been able to quickly write down the Taylor series expansion of log of 1 plus square root epsilon. So then let us look at one more example before we move on to the real problem at hand, that is the regular perturbation. I have one more example, and in this example we have a function which is 1 over 1 minus cos of epsilon to the power 3. Now we can see that if we plug epsilon equal to 0 here, f0 is not defined because cos of 0 is 1 and we have a denominator going to 0. So we will run into trouble, and then so a quick observation tells us that the Taylor series won't work. The Taylor series won't work, and then what we have is that so what can be done? So another way to look at is let us see what is the Taylor series of cos epsilon. So cos epsilon is 1 minus epsilon square by 2 plus epsilon 4 by 4 factorial minus, and so on and so forth. So 1 minus cos epsilon is epsilon square by 2 factorial minus epsilon 4 by 4 plus, and so on and so forth, right? So we have that 1 minus 1 by cos epsilon is going to be well, 1 by epsilon square by 2 minus epsilon 4 by 4 and plus, and so on and so forth, right? And we see that this is also equal to 2 by epsilon square, then divided by 1 minus epsilon square by 12 plus and so on and so forth. Right? So what we have is, so we have been able to find, notice that this factor 1 by 1 minus cos epsilon is a product of a function which is not defined. So this is not defined at epsilon equal to 0, and the second factor is a well-behaved. This is a well-behaved factor, well-behaved function at epsilon equal to 0, and we see that this is a product of singularly perturbed factor and a factor which is well-behaved. So anyway, we can still write down the series expansion here. We see that now if we were to take this series to be y, right? So this is y here, and now what we have is that our y is minus epsilon square by 12 plus epsilon 4 by some factor and so on, right? So now what we have is this factor 1 minus epsilon square by 12 plus epsilon 4 by this and so on. This is going to be let us now for the time being just look at this factor, this one. So this one is 1 plus y, right? And now if we were to now look at, so the original problem was 1 by 1 minus cos epsilon to the power 3. So now what we have is 1 by this whole factor to the power 3. So this is now 1 plus y to the power minus 3, given y to be this series that we have assumed. So so now we can start to write down again the binomial expansion. This is going to be 1 plus 3y. Well, it has a minus 3 factor, so it has to be 1 minus 3y plus 6y square minus and so on, right? So what we have is that this is 1 minus 3 minus epsilon square by 12. So now we can start to plug in the values of y. 1 minus 3 epsilon square by 12 plus and so on plus 6. Then we have the y square factor minus epsilon square by 12 plus and so on to the power 2. And then we can continue writing the factors in this power. So now we can start to expand this factor. This factor will be 1 plus epsilon square by 4, and then we can have the higher powers and so on and so forth. So important thing to see is that despite the fact that the direct Taylor series was not working in this problem, when we start plugging in the values of epsilon equal to 0, we were able to still work and figure out a Taylor series expansion of this function. And how did we do that? We were able to utilize the well-behaved function cos of epsilon, expanded 1 minus cos of epsilon, and then looked at the factor which was well-behaved and did some substitution to be able to figure out what is. So, well, I think we are just one more step remaining. So this particular Taylor series is for the well-behaved function, and then we have another function which is 2 by epsilon square sitting outside this factor. So 2 by epsilon square, right? So that is what we have. Okay, so then what we have is, we had a cube sitting, so it had to be 2 by epsilon square to the power 3. So let me now recap everything and write down the final answer to this problem. So the final answer is 1 by 1 minus cos of epsilon cube is now 2 by epsilon square whole cube. So this is 8 by epsilon 6. Then 1. Then the factor inside is 1 plus epsilon to the power 4. Epsilon square by 4 minus and so on so forth. Right? And that is the entire series expansion of this function. Okay, so I think I am all out of time at this in this module, and in the next module we will be looking at the more general form of regular perturbation, where we may or may not be able to use the power series expansion. Right. So thank you very much for listening.